Energy is the ability to do work, and we saw that as we did our lab with our work and our kinetic energy theorem, that the amount of work that we put into a system is equal to the change in the kinetic energy that takes place. And remember, that is the change in the kinetic energy, not necessarily any final or initial by itself. So let's look at our different forms of energy. The first one that we have is potential, and this is our stored energy. And we're going to be doing it with our gravitation. So this one's based on gravity. So my formula for potential energy is mass times gravity times height. And of course my unit is the joule, as it is for work. My other type of energy is kinetic, and this is energy in motion. And so my kinetic energy is based on the motion of an object, so that's 1/2 mass velocity squared, and once again the unit is the joule. So I have my two types of energy, one that's stored and one that is kinetic. And so now when I look at them together, my change in potential energy is equal to my change in kinetic energy. So that simply means this, and this is what we're going to start with. We'll get to final and initial at another time. But right now we're looking at my potential energy equal to my kinetic energy. So what does that look like in a problem? Well, let's say I have a mass of 5 kilograms. So let's put a mass of 5 kilograms here, and let's put it at a height of 10 meters. And so now this object has an ability to do work. How much potential energy does it have here, and how much kinetic energy does it have? Well, to calculate the potential energy at this height, it's going to be 5 times 9.8 times 10. And so my total potential energy is 490 joules. The amount of kinetic energy I have is 0. And it's simply because this is not moving at all, and it's at maximum height. So now as the object falls and it gets down here to the bottom, what is the potential energy at the bottom, and what is the kinetic energy at the bottom? Well, at the very bottom, once again, we're looking at a 0 meter. So that means I have 0 joules of potential energy. How much kinetic energy do I have? Well, that's going to be equal to the amount of potential energy. It's all converted. Now, we're ignoring friction. So it's all converted to 490. So now what if I were to ask you, how fast is it going? What is the velocity of the ball right before it hits the ground? Well, now I'm going to take my kinetic energy formula. So my kinetic energy is equal to 1/2 mass velocity squared. And I'm going to calculate for velocity. My kinetic energy is 490, and that is equal to 1/2. The mass is 5 v squared. So I have a velocity at the very bottom of 14 meters per second. So now let's say, what happens halfway? How much potential energy do I have, and how much kinetic energy do I have at the halfway point? Well, that's going to be at the 5 meter mark. And so all I have to do is 5 times 9.8 times 5, and I'm going to get 245 joules. And that means the object has gained 245 joules of kinetic energy. And that makes sense, because if we're halfway down, it's going to be half the amount of energy of the 490. Now, what is the velocity halfway down? Well, once again, my velocity is going to be, let's change that. My kinetic energy is 245, and that's going to be equal to 1/2 the 5 times the v squared. And so my velocity halfway down is 9.9 meters per second. Another way we calculate is with a pendulum, and I'm going to be showing you this in class. When you raise a pendulum, so let's say it goes from here to this position here. When you raise the pendulum, the distance that it travels is not this distance here. The distance that travels is going to be from this point to this point. So my distance is this height here. And so as I raise a pendulum, and later on we'll do it with the angle, But right now we're going to look at the height at which I take it from. At the very lowest position of a pendulum, your potential energy is 0. If it's not moving at all, then your kinetic energy is 0. But as I move and give it height, now I have a potential energy. And the potential energy is based on, obviously, the mass, the gravity, and the height at which I move it. So let's say the mass of this pendulum, so let's give it a mass of 50 grams. And let's move it a height of 10 centimeters. Let's displace it 10 centimeters, and once again, that's how high it goes. So now what's its potential energy? Well, if I multiply mass times gravity times height, I'm going to get 0.049 joules of potential energy. Don't forget to convert your 50 grams to kilograms, and don't forget to convert your 10 centimeters to meters. So as I move this pendulum up, it has a potential energy of 0.049 joules. The kinetic energy, since it's at its highest point, it's all stored, so your kinetic energy at this point is 0. But now as it moves down, I'm going to change color as it moves down, now I have a velocity. So what is the velocity of the object at the very bottom? Well, at the very bottom, my kinetic energy is 0.049 joules. So I'm going to do the math up here. So 0.049 is equal to 1/2 your mass, which is 0.05 times my velocity squared. And so the velocity of the pendulum at the very bottom of its path is 1.4 meters per second. As this pendulum swings back up, as it swings up here, it converts back to its potential energy. And as it continues to swing back and forth, it will continue to convert from potential to kinetic. Now eventually the pendulum will stop. And the reason that is going to happen is because of the friction that occurs and the energy that's lost as heat, the energy that may be lost as sound or in the mechanism or whatever it happens to be. But the pendulum, but as it swings back and forth, it converts its potential to kinetic in that manner. So let's do one more problem. Let's say I have an object, and let's give it a mass of 2 kilograms. And let's just throw it straight up. And what I want to know is, well, let's say it goes up to a height, this goes to this point, and so it has a height of 14 meters. If it takes it to a height of 14 meters, what's its potential energy at the top? Well, once again, that's going to be mass times gravity times height. And so that's going to be equal to 274.4 joules. How much kinetic energy does it have at the top? It's going to have 0. As it falls back down, it's going to reconvert just like we did here. It's going to convert back to its kinetic. So what was the velocity that the object was tossed with? Well, if I know that at the bottom when it comes back down, if I know that it's kinetic energy, let's put it over here. If I know its kinetic energy is going to be 274.4 at the bottom on the way back down, all points are equal as we learned in our free fall. So 274.4 is equal to 1/2 2 times velocity squared. So that means the velocity at the bottom of the path is going to be 16.57 meters per second. So I can calculate all sorts of things with this kinetic energy and potential energy. Now one of the next things that we're going to do, and this will be coming soon, but one of the next things that we're going to do is we're going to be looking at our roller coasters. So let's say I have a roller coaster, and in that roller coaster I have different heights. And then of course this is at the very bottom, and then I have a height here. So what we're going to be able to do is we're going to see how roller coasters calculate the speed at which they travel. And once again, that's going to be based on our delta kinetic energy is equal to my change in potential energy.